extreme values of functions on unbounded intervals and limit at infinity. Hi friends, welcome back. We have discussed maximum and minimum of mathematical functions in the previous session. The method of finding absolute maximum and minimum of continuous functions on closed intervals has been discussed in the previous session. Now, we are going to extend the domain of continuous functions to unbounded sets and examine whether absolute extrema can be evaluated for such functions. Absolute extrema of functions with one local extremum. We recall that a function f has a local maximum or relative maximum value at an interior point x naught of its domain if f of x naught is greater than or equal to f of x for all x in some open interval containing x naught. A function f has a local minimum or relative minimum value at an interior point x naught of its domain if f of x naught is less than or equal to f of x for all x in some open interval containing x naught. We will see that if a continuous function has only one relative extremum on a finite or infinite interval, then that relative extremum must necessarily be an absolute extremum. While observing the graph of f of x equal to -1 minus x minus 3 square, or by seeing f dash of x is equal to -2 into x minus 3 is equal to 0 implies x is equal to 3, we obtain that it has only one relative extremum at x equal to 3 and the value is f of 3 is equal to -1. All other f of values are less than -1. In this example, the only relative extremum becomes absolute extremum. So, we inquire whether in general, if a continuous function has only one relative extremum on a finite or infinite interval, then that relative extremum be necessarily an absolute extremum. For this, suppose that f has a relative maximum at x naught in an interval and there are no other relative extremum of f on the interval. If f of x naught is not the absolute maximum of f on the interval, then the graph of f has to make an upward turn somewhere on the interval to rise above f of x naught. However, this cannot happen because in the process of making an upward turn, it would produce a second relative extremum. Without giving a theoretical proof, we record this in the following theorem. Theorem: suppose that f is continuous and has exactly one relative extremum on an interval I, say at x naught, then A, if f has a relative minimum at x naught, then f of x naught is the absolute minimum of f on I, and B, if f has a relative maximum at x naught, then f of x naught is the absolute maximum of f on I. Absolute extrema on infinite intervals. A continuous function may or may not have absolute extrema on an infinite interval. For example, the function f of x equal to x has no extremum on the entire real line. In order to discuss the existence of absolute extrema of a continuous function f on minus infinity to plus infinity, we have to take into consideration the behavior of f of x as x goes to minus infinity and as x goes to plus infinity. With this aim in mind, we are now going to study the behavior of a function f of x as the value of the variable x increase without bound, that is, the behavior of f of x if x moves far away from the origin along the x axis to the right hand side of x axis, which we write by x goes to plus infinity or simply by x goes to infinity. We also study the behavior of a function f of x as the value of the variable x decrease without bound, that is, the behavior of f of x when x moves far away from the origin along the x axis to the left hand side of x axis, which we write by x goes to minus infinity. Note that the symbol infinity does not represent a real number and we cannot use it in arithmetic in the usual way. The behavior of a function f of x as x increases without bound or decreases without bound is sometimes called the end behavior of the function. As an example, by looking at the graph of f of x equal to 1 by x, when the values of the variable x increase without bound, we see that the values of the function approaches 0, but never takes the value 0. We denote this by writing limit x going to plus infinity 1 by x is equal to 0. Also, when the values of the variable x decrease without bound, the values of the function approaches 0, but never takes the value 0. We denote this by writing limit x going to minus infinity 1 by x is equal to 0. Formally, we say that f of x has the limit L as x approaches infinity, or f of x has the limit L at infinity, and write limit x going to infinity f of x is equal to L if for every number epsilon greater than 0 there exists corresponding number m such that modulus of f of x minus L is less than epsilon if x is greater than m. Similarly, we say that f of x has the limit L as x approaches minus infinity, and write limit x going to minus infinity f of x is equal to L if for every epsilon greater than 0 there exists corresponding number n such that modulus of f of x minus L is less than epsilon if x is less than n. By looking at the graph of f of x is equal to 1 by x, we have observed that limit x going to infinity 1 by x is equal to 0. Now, we are going to confirm this using the definition of limit at infinity. Let epsilon greater than 0 be given. We must find a number m such that modulus of 1 by x minus 0, that is equal to modulus of 1 by x is less than epsilon for all x greater than m, say condition 1. Take m is equal to 1 by epsilon, then x greater than m implies x is greater than 1 by epsilon. As both sides of the inequality are positive, their reciprocals are related by the inequality epsilon is greater than 1 by x. Again, since 1 by x is positive, this inequality implies epsilon is greater than modulus of 1 by x. Hence, condition 1 holds. This proves that limit x going to infinity 1 by x is equal to 0. We now show that limit x going to minus infinity 1 by x is also equal to 0. Let epsilon greater than 0 be given. We must find a number n such that for all x modulus of 1 by x minus 0, that is modulus of 1 by x is less than epsilon if x less than n. As epsilon is a positive number, 1 by epsilon is also a positive. Hence, minus 1 by epsilon is a negative number. We let n is equal to minus 1 by epsilon. Then, x less than n implies x is less than minus 1 by epsilon. Now, both x and minus 1 by epsilon are negative numbers, and hence their reciprocals are related by the inequality 1 by x is greater than minus epsilon, that is epsilon is greater than minus 1 by x. Here we stress the point that the inequality is getting reversed due to the presence of negative number. Now, the positive numbers epsilon and minus 1 by x are related by epsilon is greater than minus 1 by x, and minus 1 by x is equal to modulus of 1 by x implies that epsilon is greater than modulus of 1 by x. Hence, condition 2 holds. This proves that limit x going to minus infinity 1 by x is equal to 0. To find the limit of function at infinity, there is no need to use the definition itself. The following algebraic properties of limit of functions at infinity will ease our job of finding limits at infinity. These basic laws of limit of functions are analogous to the basic laws of limit of functions at a finite point. Learners are asked to fill up the gaps by providing the proofs. Properties of limits as x goes to plus or minus infinity. The following rules hold if limit x goes to plus infinity f of x is equal to L, and limit x goes to plus infinity g of x is equal to m, where L and m are real numbers. 1. Sum rule: limit x going to plus infinity f of x plus g of x is equal to L plus m. 2. Difference rule: limit x going to plus infinity f of x minus g of x is equal to L minus m. 3. Product rule: limit x going to plus infinity f of x into g of x is equal to L into m. 4. Constant multiple rule: limit x going to plus infinity k into f of x is equal to k into L for any number k. 5. Quotient rule: limit x going to plus infinity f of x by g of x is equal to L by m if m is not equal to 0. And 6. Power rule: if m and n are integers, then limit x going to plus infinity f of x to the power m by n is equal to L to the power m by n, provided L to the power m by n is a real number. Similar results hold if we replace limit x going to plus infinity by limit x going to minus infinity. As an application of properties of limits, we evaluate limit x going to plus infinity 5 plus 1 by x. Limit x going to infinity 5 plus 1 by x is equal to limit x going to infinity 5 plus limit x going to infinity 1 by x using sum rule, which is equal to 5 plus 0 and which is equal to 5. As another example, we evaluate limit x going to minus infinity pi root 3 by x square. We write limit x going to minus infinity pi root 3 by x square is equal to limit x going to minus infinity pi root 3 into 1 by x square. Applying the product rule, we obtain limit x going to minus infinity pi root 3 by x square is equal to limit x going to minus infinity pi root 3 into limit x going to minus infinity 1 by x square. Now, using the power rule, we obtain limit x going to minus infinity 1 by x square is equal to limit x going to minus infinity 1 by x whole square, which is equal to 0 square, that is 0. Hence, limit x going to minus infinity pi root 3 by x square is equal to pi root 3 into 0, that is 0. Limits of rational functions as x goes to plus or minus infinity. To determine the limit of a rational function as x goes to plus or minus infinity, we divide the numerator and denominator by the highest power of x in the denominator. What happens then depends on the degree of the polynomials involved. In order to understand the method of finding limits when the numerator and denominator are of same degree, we consider the problem to evaluate limit x goes to infinity 5x square plus 8x minus 3 whole divided by 3x square plus 2. The highest power of x in the denominator is x square. By dividing both numerator and denominator by x square, we get limit x going to infinity 5x square plus 8x minus 3 whole divided by 3x square plus 2 is equal to limit x going to infinity 5 plus 8 by x minus 3 by x square whole divided by 3 plus 2 by x square, which is equal to 5 plus 0 minus 0 whole divided by 3 plus 0, that is 5 by 3. By looking at the graph of f of x is equal to 5x square plus 8x minus 3 whole divided by 3x square plus 2, we may get a feel that the graph touches the line y is equal to 5 by 3 when x approaches infinity. Now, consider the problem to evaluate limit x goes to minus infinity 11x plus 2 whole divided by 2x cube minus 1, where the degree of the denominator is bigger than that of the numerator. The highest power of x in the denominator is x cube. By dividing both numerator and denominator by x cube, we get limit x going to minus infinity 11x plus 2 divided by 2x cube minus 1 is equal to limit x going to minus infinity 11 by x square plus 2 by x cube whole divided by 2 minus 1 by x cube, which is equal to 0 plus 0 divided by 2 minus 0, that is 0. By looking at the graph of f of x is equal to 11x plus 2 whole divided by 2x cube minus 1, you may get a feel that the graph touches the line y is equal to 0, that is the x axis, when x approaches infinity. In the previous examples, we have finite limit values when x approaches infinity. We shall now discuss examples when the values of f of x increase or decrease without bound as x goes to plus infinity or as x goes to minus infinity. If f of x increase without bound as x goes to plus infinity, we denote it by limit x going to plus infinity f of x is equal to plus infinity. For example, by looking at the graphs, we can see that limit x going to infinity x is equal to plus infinity and limit x going to infinity x square is equal to plus infinity. If f of x increase without bound as x goes to minus infinity, we denote it by limit x going to minus infinity f of x is equal to plus infinity. For example, by looking at the graph, we can see that limit x going to minus infinity x square is equal to plus infinity. If f of x decrease without bound as x goes to plus infinity, we denote it by limit x going to plus infinity f of x is equal to minus infinity. For example, by looking at the graph, we can see that limit x going to plus infinity minus x square is equal to minus infinity. If f of x decrease without bound as x goes to minus infinity, we denote it by limit x going to minus infinity f of x is equal to minus infinity. For example, by looking at the graphs, we can see that limit x going to minus infinity x is equal to minus infinity. Consider an example to evaluate limit x going to minus infinity 2x square minus 3 whole divided by 7x plus 4, where the degree of numerator greater than degree of denominator. The highest power of x in the denominator is x. By dividing both numerator and denominator by x, we get limit x going to minus infinity 2x square minus 3 by 7x plus 4 is equal to limit x going to minus infinity 2x minus 3 by x whole divided by 7 plus 4 by x. As x goes to minus infinity in the numerator, 3 by x goes to finite number 0, while 2x goes to minus infinity. In short, the numerator goes to minus infinity when x goes to minus infinity. Also, as x goes to minus infinity in the denominator, 4 by x goes to the finite number 0, while 7 becomes unaltered. In short, the denominator goes to 7 when x goes to minus infinity. So, the ratio 2x square minus 3 divided by 7x plus 4 approaches minus infinity. That is, limit x going to minus infinity 2x square minus 3 whole divided by 7x plus 4 is equal to minus infinity. This can be visualized in the graph of the function f of x is equal to 2x square minus 3 whole divided by 7x plus 4. As another example, we evaluate limit x going to minus infinity minus 4x cube plus 7x whole divided by 2x square minus 3x minus 10. The highest power of x in the denominator is x square. By dividing both numerator and denominator by x square, we get limit x going to minus infinity minus 4x cube plus 7x whole divided by 2x square minus 3x minus 10 is equal to limit x going to minus infinity minus 4x plus 7 by x whole divided by 2 minus 3 by x minus 10 by x square. As x goes to minus infinity in the numerator, 7 by x goes to the finite number 0, while minus 4x goes to minus infinity. In short, the numerator goes to minus infinity. When x goes to minus infinity, also as x goes to minus infinity in the denominator, both 3 by x and 10 by x square goes to 0, while 2 becomes unaltered. In short, the denominator goes to 2 when x goes to minus infinity. So, the ratio goes to infinity. Hence, limit x going to minus infinity minus 4x cube plus 7x whole divided by 2x square minus 3x minus 10 is equal to infinity. Let us now come back to the discussion of finding absolute extrema of functions, this time giving attention to the unbounded intervals also. Absolute extrema on infinite intervals. We have noted that a continuous function may or may not have absolute extrema on an infinite interval. For example, consider the function f of x is equal to x. However, certain conclusions about the existence of absolute extrema of a continuous function f on minus infinity to plus infinity can be drawn from the behavior of f of x as x goes to minus infinity and as x goes to plus infinity. If f is continuous everywhere on the real line, we consider 4 cases where conclusions about the existence of absolute extrema can be drawn. Case 1, when limit x goes to minus infinity f of x is equal to plus infinity and limit x goes to plus infinity f of x is equal to plus infinity, then f has an absolute minimum, but no absolute maximum on the interval minus infinity to plus infinity. For example, for the function f of x is equal to x square, limit x go into minus infinity f of x is plus infinity and limit x go into plus infinity f of x is plus infinity, and f has an absolute minimum at 0, but no absolute maximum on the interval minus infinity to plus infinity. Case 2, when limit x go into minus infinity f of x is minus infinity and limit x go into plus infinity f of x is minus infinity, then f has an absolute maximum, but no absolute minimum on the interval minus infinity to plus infinity. For example, for the function f of x is equal to minus x square, limit x go into minus infinity f of x is equal to minus infinity and limit x go into plus infinity f of x is minus infinity, and f has an absolute maximum at 0, but no absolute minimum on the interval minus infinity to plus infinity. Case 3, when limit x go into minus infinity f of x is equal to minus infinity and limit x go into plus infinity f of x is equal to plus infinity, then f has neither an absolute maximum nor an absolute minimum on minus infinity to plus infinity. For example, for the function f of x is equal to x cube, limit x go into minus infinity f of x is equal to minus infinity and limit x go into plus infinity f of x is equal to plus infinity, and f has neither an absolute maximum nor an absolute minimum on the interval minus infinity to plus infinity. Case 4, when limit x go into minus infinity f of x is plus infinity and limit x go into plus infinity f of x is minus infinity, then f has neither an absolute maximum nor an absolute minimum on the interval minus infinity to plus infinity. For example, for the function f of x is equal to minus x cube, limit x go into minus infinity f of x is plus infinity and limit x go into plus infinity f of x is minus infinity, and f has neither an absolute maximum nor an absolute minimum on the interval minus infinity to plus infinity. Absolute extrema of polynomials. What can we say about the existence of absolute extrema on the interval minus infinity to plus infinity for polynomials? Let us analyze. If p of x is a polynomial of odd degree, then limit x go into minus infinity p of x and limit x go into plus infinity p of x have opposite signs. One is plus infinity and the other is minus infinity. So, there are no absolute extrema. We have already observed this behavior for x and x cube, which are polynomials of odd degree. If p of x is of even degree, then limit x go into minus infinity p of x and limit x go into plus infinity p of x have the same sign, that is both plus infinity and minus infinity. If the leading coefficient, that is the coefficient of highest power term, is positive, then both limits are plus infinity and there is an absolute minimum, but no absolute maximum. If the leading coefficient is negative, then both limits are minus infinity and there is an absolute maximum, but no absolute minimum. These observations have already been yielded for x square and minus x square, simple polynomials of even degree. As another example, let us inspect p of x is equal to 3 x to the power 4 plus 4 x cube for absolute extrema. Since p of x has even degree and the leading coefficient is positive, p of x goes to plus infinity as x goes to plus or minus infinity. Thus, there is an absolute minimum, but no absolute maximum. This absolute minimum occurs at a critical point of p of x. Since p of x is differentiable everywhere, we can find all critical points by solving the equation p dash of x is equal to 0. This equation is 12 x cube plus 12 x square equal to 12 x square into x plus 1, which is equal to 0, from which we conclude that the critical points are when x is equal to 0 and x is equal to minus 1. Evaluating p at these critical numbers, we have p of 0 is equal to 0 and p of minus 1 is equal to minus 1. Of these, minus 1 is the minimum value, therefore, p has an absolute minimum of minus 1 at x is equal to minus 1. The method of finding absolute extrema of a function on unbounded intervals is: step 1, determine the critical points of f in the interval I. Step 2, evaluate f at all critical points. If I has a left endpoint A or a right endpoint B, evaluate the function value at those points. Step 3, if the left end of the interval is not a finite real number, observe the behavior of the function as x goes to minus infinity. Similarly, if the right end of the interval is not a finite real number, observe the behavior of the function as x goes to plus infinity. And step 4, identify absolute extrema if they exist. For example, let f of x is equal to x to the power 4 minus 4 x cube minus 2 x square plus 12 x be defined over the entire real line. We shall look for absolute extrema of f on the interval minus infinity to plus infinity. Here the polynomial f of x is equal to x to the power 4 minus 4 x cube minus 2 x square plus 12 x is of even degree, and since the leading coefficient, that is the coefficient of x to the power 4, is 1, which is positive. So, both limits, limit x going to minus infinity f of x and limit x going to plus infinity f of x are plus infinity, and there is an absolute minimum, but no absolute maximum. To determine the absolute minimum, we find critical points as follows: f dash of x is equal to 4 x cube minus 12 x square minus 4 x plus 12. Hence, to find critical points, we equate f dash of c is equal to 0, that is 4 c cube minus 12 c square minus 4 c plus 12 is equal to 0, that is 4 c square into c minus 3 minus 4 into c minus 3 is equal to 0, that is 4 into c minus 3 into c square minus 1 is equal to 0, that is c minus 3 into c minus 1 into c plus 1 is equal to 0, that is c is equal to minus 1, 1 or 3. Thus, c is equal to minus 1, 1 or 3 are critical points. Now, f of minus 1 is equal to minus 9, f of 1 is equal to 7, f of 3 is equal to minus 9. Thus, we have found all local extrema. Limit x going to minus infinity f of x is equal to limit x going to minus infinity x to the power 4 minus 4 x cube minus 2 x square plus 12 x, that is equal to limit x going to minus infinity x to the power 4 into 1 minus 4 by x minus 2 by x square plus 12 by x cube, which is equal to limit x going to minus infinity x to the power 4 into limit x going to minus infinity 1 minus 4 by x minus 2 by x square plus 12 by x cube. As x goes to minus infinity, 4 by x, 2 by x square and 12 by x cube all go to 0. So, that limit x going to minus infinity 1 minus 4 by x minus 2 by x square plus 12 by x cube is equal to 1. Further, limit x going to minus infinity x to the power 4 is equal to limit x going to minus infinity x whole to the power 4, which is equal to infinity. Hence, limit x going to minus infinity f of x is equal to infinity. Similarly, limit x going to infinity, f of x is equal to infinity. Hence, f does not have an absolute maximum. However, f has an absolute minimum minus 9 attained at 2 points minus 1 and 3. Let us now look for absolute extrema of the function f of x is equal to x cube minus 3x square plus 4 on the intervals a minus infinity to plus infinity and b 0 to plus infinity. A, because f is a polynomial of odd degree with leading coefficient positive, it follows that there are no absolute extrema on the interval minus infinity to plus infinity. B, since limit x going to plus infinity, x cube minus 3x square plus 4 is equal to plus infinity, we know that f cannot have an absolute maximum on the open interval 0 to plus infinity. However, the limit x going to 0 plus x cube minus 3x square plus 4 is equal to 4 is a real number. So, there is a possibility that f may have an absolute minimum on this interval. In this case, it would have to occur at a critical point, which suggests that we look for solutions of the equation f dash of x is equal to 0. But f dash of x is equal to 3x square minus 6x, which is equal to 3x into x minus 2. So, f has a critical numbers x is equal to 0 and x is equal to 2. However, the only critical number inside the open interval 0 to plus infinity is x is equal to 2. Therefore, f has at most one extremum. Since f double dash of x is equal to 6x minus 6, we have f double dash of 2 is equal to 6, which is greater than 0. So, a relative minimum occurs at x is equal to 2 by the second derivative test. Thus, f of x has an absolute minimum at x is equal to 2, and this absolute minimum is f of 2, which is equal to 0. Let us now look at the rational function f of x is equal to x minus 1 whole divided by x square plus 1. We have f dash of x is equal to x square plus 1 into 1 minus 2x into x minus 1 whole divided by x square plus 1 whole square, which is equal to minus x square plus 2x plus 1 whole divided by x square plus 1 whole square. F dash of x is equal to 0 implies x square minus 2x minus 1 is equal to 0. So, that x is equal to 2 plus or minus square root of 2 square plus 4 whole divided by 2, which is equal to 1 plus or minus square root of 2 are the local extrema. F of 1 plus root 2 is equal to 1 by 2 root 2 plus 2, which is approximately equal to 0.207, and f of 1 minus root 2 is equal to minus 1 divided by 2 times root 2 minus 2, which is approximately equal to minus 1.207. Limit x going to infinity f of x is equal to limit x going to infinity x minus 1 whole divided by x square plus 1, which is equal to limit x going to infinity 1 by x minus 1 by x square whole divided by 1 plus 1 by x square equal to 0 by 1, which is equal to 0. Similarly, limit x going to minus infinity f of x is equal to 0. Thus, f of x going to 0 either if x increase without bound or if x decrease without bound. Hence, f takes maximum value 1 by 2 root 2 plus 2, which is approximately equal to 0.207 at x is equal to 1 plus root 2, and f takes minimum value minus 1 by 2 root 2 minus 2, which is approximately equal to minus 1.207 at x is equal to 1 minus root 2. It can be observed from the graph that f attains local maximum and minimum at no other places. Let us summarize now. We started with functions defined on unbounded domains. The end behavior of f are analyzed using the concept of limit at infinity, which help us to look for absolute maximum and minimum of functions on the entire domain. Hope you have enjoyed the session. See you for the next session. Have a nice day.